often is the case, I would encourage you guys to try to keep your, I know you need to take some notes, but a lot of what I'm going to show you in the beginning here is more conceptual than anything else, so try to keep your eyes up more than down. Okay, I'm being a little bit flip when I say the sphere mechanical is easy. You know, technically it's that, you know, it's a circle. But that's not the whole story, because that circle doesn't give you any real cues. You don't know where it's sitting on the ground. You don't know exactly how it relates to the box that it's in. You see what I mean? So you need to know these things, how it's sitting in that box and how it's resting on the ground before you can cast the shadow intelligently. So here's a couple things I would say. First of all, start off with a cube. That would be the first thing. Start off with a cube. I'd even suggest you start off with a cube in one-point perspective. And here's why. So start off with a cube in one-point perspective, because if you can, you've just found five key points on your sphere. Actually, technically, 7. You see what I mean? Because you know it has to contact all those points, plus you know where the center is. Now when you guys are doing this, here's the challenge. The ellipses are a better indicator of the size than the actual where it hits these points. And this may not be immediately clear, so let me explain. If we were drawing a hemisphere, and you asked us to find the exact top of it, and it was from the side, we'd say, oh, that's the exact top. And if we were seeing it from above, we'd say that. Now, did we do this in this class? Okay. Oh, that's why. I'm saying that. Okay. So, you guys, I'll do it very quickly, just so we know. We did this already in class, but now I'll make the point. Okay, so this top point of what would be a sphere is not actually on the outer perimeter, and the same thing is going to be true for your sphere. You're going to see, if you're looking down on the sphere, you're going to see a little point here, you're going to see a little point here, but technically those would be the only, oh, and actually, I'm sorry, and you'd see a point about here. Technically, those 3 points are the only points you'd see on the surface where it touches the cube. These other ones would be on the underside where you can't see it, on the far side where you can't see it, and on the back side where you can't see it. You see what I mean? So you don't really have to calculate all those points, but because those things aren't really the true indicator of the size of the sphere, like if you go to draw it with a compass, you wouldn't want to measure from there to there because that's not accurate. So a better way of doing this, of determining what the size of your sphere should be, is to do this. Imagine instead if you took your cube and you did that through the center, and you imagined 2 planes, then what you would end up with is something kind of like this. You see what I mean? Now these ellipses, they are the size that you want. You see what I mean? the actual size of the sphere. And they will sweep slightly outside of those contact points that we discussed. Does that make sense to you guys as a context, or as a concept, I should say? All right. Now, I need to familiarize you guys with a concept called the drift line. All right, what the concept of the drift line is about is this, is if you have an object like this, let's say a sphere, and you imagine stuff like, say, a water drop falling on it, and imagine there's no water or surface tension, and it rolling across the surface, getting to the midpoint, and instead of like the surface tension of going like this, imagine it dropped straight down to the ground. Or if it hit here and it went, and then it dropped straight down to the ground. If you did that on all sides, you'd end up with something like this. An ellipse about that big, centered around the touch point. Not centered, but you know what I mean. Okay, now, so this is called the drip line.
Drip or grip?
Drip. And it's important because it's critical. It's critical to casting a shadow. You guys, to save some drawing time, because this is just conceptual, what you end up with ostensibly, if you did this, is, imagine if instead of dripping, imagine you had a light directly above the sphere, and it's projecting downwards. And you get this kind of effect. But then do you see that you also, between these two ellipses, you get a series of Delilahs. Now it's just like a cylinder. Same exact problem. Now there's one additional wrinkle though. With the cylinder, those Delilahs stay at a consistent height. Okay? What happens with a sphere is something like this. No matter what angle the light is coming in at, no matter what angle, because it's a sphere, there is always a given plane within that sphere that is perfectly perpendicular to the light, no matter where it's coming from.
So it's like the Earth and the Sun.
Right, exactly like the Earth and the Sun. Exactly. So there's always a perpendicular plane. Now here's the part that's kind of hard for people to understand. But this is the truth. Do you see that if you have a light hitting a sphere like this, that if I set it up at the perfect angle, there would be no difference at all in between the shadow of the sphere here and the shadow of the hemisphere. They would cast identical shadows if you match them up perfectly. You see what I mean? Now that's a key concept because usually when a light hits a sphere, it's hitting at some angle to us. It's not convenient that it's always directly overhead or anything like that. And so when that happens, we end up getting something like this. We have, this is the back side of the ellipse, this is the front side of the ellipse. And you have different sized Delilahs and a different drip line. Because you see that if the ellipse is doing this, well now the drip line's only that big around, kind of. You see what I mean? So what I sometimes recommend people think about when they're casting the shadow of a sphere is I recommend that they actually think of this. If this were the top of the hemisphere, like that, okay, and this were shorter, you could theoretically line up a same-sized sphere and cast the exact same shadow. You see what I mean? So this is a useful way to think about, provided the light was coming in perpendicular to this surface, you could cast the same basic shadow. All right, does that make sense to everyone? Yeah. This here? I'm about to. No, that's good. It means, now, I'm going to do this in a very basic sense here.